Hello, and welcome to video lesson 17, where we're going to talk about stress on oblique planes. Our learning objectives for this session are to resolve forces or attractions, another name for forces, into normal and oblique components, oblique being shear, resting in an oblique plane. We're going to compute the areas of oblique cross sections. And then once we've done those things, we're going to calculate stresses, in other words, normal and shear stresses on oblique planes. Now, this is a section that occurs really early in Beer and Johnston, but I've saved it for later because this is very closely related to the idea of stress transformation, which is really a unit that's later in the course. And I think that focusing too much on oblique planes early can make it a little less easy to catch on to the course. So there's a reason for saving this section for right now. So for the general case, we're going to study that first, and then we're going to study some specific cases of this transformation. I wanted to show you the results for the general case first. Let's consider a bar that has an axial loading of P on the bar. And rather than calculate the stresses on the cross-sectional plane, I'd like to know what the stresses are on this oblique plane. And maybe that's because I had an element fail and I needed to weld it back together, or I needed to epoxy a bridge back together or something, and I needed to do a repair. And I might need to know, is the material that I'm using going to be good enough for this repair? So in order to do that, I would need to know what stresses exist on this particular plane. So if I want to do that, I would need to be able to calculate the area of this plane, and that's actually pretty easy if I know its angle of inclination theta. So the area of this oblique plane, I'm going to call that A oblique, but that's equal to A over sine theta, where A is our cross-sectional area. Well, as soon as I start rotating the plane, I now no longer have P completely perpendicular to the plane either. So I'm going to need to resolve the force P into its components. Its normal component to the plane is P sine theta, and its component that lies in the plane, which would be responsible for shearing stresses on this oblique plane, would be P cosine theta. So if I'm looking to calculate the normal stress on the oblique plane, I would calculate that as the normal component to the plane n divided by the area of the oblique plane. And that ends up being P sine theta over A over sine theta. And then when I simplify all of that, I end up with sigma oblique, the normal stress on an oblique plane, equal to P over A times sine squared of theta, where theta was that angle of inclination. Similarly, I could compute oblique shear stress as B over A for the plane. I'll just note that that's A oblique. So that would be equal to P cosine of theta divided by A over sine theta. And when I simplify, I end up with tau oblique equal to P over A times sine theta times cosine theta. Now, for some of you who are keen on double angle transforms, you might see that this starts to suggest something circular. Some circular parametric function for maybe normal and shear stress as I change the angle theta. So we'll take a look at that. We'll keep that in the back of our minds. And we'll take a look at a particular example. So for this particular bar, I've got a plate of steel, 1 inch by 6 inches, and I'm putting a loading of 36 kips at the end, and I want to know what the stresses are on planes A, BB, CC, and DD. So for plane AA, theta is equal to 0 degrees. Sorry, theta is equal to 90 degrees. Theta is equal to 90 degrees because I have the right angle right there. So for plane AA, I have theta AA equal to 36 kips over 6 square inches times sine squared of 90. Well, sine of 90 is 1, so I end up with 6 KSI. And when I do tau AA for theta equal to 90, I end up with 36 kips over 6 square inches times sine of 90 times cosine of 90, and that gives me 0 KSI, as I would expect, because for plane AA, that is the cross-sectional plane, and you can see that these formulas that we just derived give us what we should expect for the case of plane AA. Now let's move on to plane BB. We've got theta equal to 60 degrees. And then we would just apply our formulas. Sigma BB is equal to 6 KSI times sine squared of 60, and that would be 4.5 KSI. And then tau BB is 6 KSI times sine of 60 degrees times cosine of 60 degrees, and that gives me 2.598 KSI. Well, if I move on to plane CC, theta would be 45 degrees. So this angle here is 45, and so is this angle here. So for theta equal to 45 degrees, I would have sigma CC equals 6 KSI times sine squared of 45, and that's 3 KSI. And tau BC is equal to 6 KSI times sine of 45 times cosine of 45, which is also 3 KSI. And then for plane DD, I would have sigma DD equal to 6 KSI times sine squared of 30 equal to 1.5 KSI. And then when I do tau DD for the shear stress, I would have 6 KSI times sine of 30 times cosine of 30, or 2.598 KSI. Well, these are interesting results. Maybe we can make some sense out of these results in a graphical way, and that's what I'm going to do here. So if I was to take a look at the results for thetas of different for different angles of inclination, I'd have an angle of inclination of 30 degrees for this one, for 45 degrees here, for 60, and then for 90 degrees for theta. And if I was to take a look at where these lie, I would have a circle swept out. So if I rotate the plane by 30 degrees, if I have a 30-degree angle of inclination, I end up going 60 degrees around the circle. And then if I have 45 degrees, I end up going 90 degrees around the circle. And then if I have an angle of inclination of 60 degrees, I end up going 120 degrees around the circle. And then if I have an angle of 90 degrees, I go 180 degrees around the circle, starting from the origin. So we can see that if I was to transform stresses, I would sweep out a circle. And whenever I rotated my plane by an angle theta, I would sweep an angle of 2 theta along the circle. So to just wrap up what we should take away from this lesson, the most important thing that you should remember is the process of how we did the stress transformation. You should realize that whenever we calculated stresses on a new oblique plane, we had to resolve the force result into its resultant components, and we had to come up with a new area because we now have an inclination there. And we get the stresses the same way we always have, using the same definitions we always have. We just have to use new components for normal and for shear tractions, or those would be the force components that are acting on the plane. And we have to use the area of the oblique plane instead of the cross-sectional area. And when we do that, that will leave us with a very straightforward way of computing stresses on new oblique planes. That's it for video lesson 17.